Yo, what's up, guys? Today we're going to be doing a calculus tutorial on the chain rule. Um, the chain rule is basically just it's the fundamental theorem of calculus, but for derivatives. It is probably the most important rule for finding derivatives besides the power rule. And you'll find as we continue to do problems in this, um, that it's very, very, very similar to the derivative or the power rule. Um, So yeah, let's get started. If you know how to take a power rule and you know how to use it, you'll know how to do this. You know, there are problems out there. Most problems actually involve other rules, but the basics for a problem like right in front of us actually, you just need to know power rule and then chain rule. But they're very similar. The chain rule has like one extra caveat to the power rule. So let's get started. So first thing you do is you apply power rule to this whole thing. Um, and by doing that, to do that, you just don't care about what's inside, and you just place a 3 out in the front, and then you place this exponent out in front, and then -1 from the exponent. So that'll look like this. You see how I -1 from that and placed the 3 out in front. Next, you need to multiply. You don't add and you don't subtract or divide. You multiply. And this time, you only take the derivative of what's inside. You don't worry about this exponent. So this is your answer. This is all you have to do. You do the power rule with this thing. You don't care about what's inside, and then you multiply by the derivative of what's inside, not caring about the exponent. Okay, let's move on to the next one. So this one uses quotient rule, I see. It's still going to be the same idea, do power rule and then take the derivative of the inside. Let me see if I can write that more straight. There you go. And you see I'm -1 from the 8 and put the 8 on the front times. And then let's do low D high minus high D low. You should kind of know what that means. If you don't, skip 10 seconds in the future on the video in the future, and just skip this. So you take just the low value. You don't take a derivative. Then you take the derivative of the top, and then you do the vice versa. You just have the top times the derivative of the low, and then you square the low. So that'll look like this. So 4x minus 1 times the derivative of the top, which is just 3, minus the top, which is 3x minus 2, times the derivative of the low, which is just 4. And then you all over 4x minus 1 squared. And this is your answer. Um, AP, any AP exam should be able to take this as an answer. The only reason I can think of them not doing it is that them seeing that this is a pretty basic, because it's just being multiplied by a number. It's pretty basic to just, especially since 4 times 3 and 3 times 4, you should know that that equals 12, because they're just, it's commutative. So I'm just gonna say, yeah, that's what happens, especially with the minus. So the 12s cancel out, and then 3 times -1 is -3 minus -8, which is positive 5 over 4x minus 1 squared times 8 times 3x minus 2 over 4x minus 1. This is for sure an answer. If you wrote this on any test, you'd get a score for it. You get it the right answer. You get it correct, basically. However, there is another thing that you can do that's maybe not obvious at first, but it's pretty, it's just algebra. Um, since this isn't like in a square or anything, or it's not in a square root, or it's not on the bottom, you can just multiply this and the 8, so you get 40, and then not, and then you should be able to see that uh, the 7 exponent applies to just the top and the bottom. It's just 3x minus 2 to the 7th over 4x minus 1 to the 7th. That's just an exponent rule. And then we can just multiply together these, so we just keep 3x minus 2 to the 7th on top. But since we have 2 and we're multiplying it by 4x to minus 1 to the 7th, it's gonna add and make 4x minus 1 to the ninth. Uh, I hope you saw how that worked, because I mean that's not really important, but that's just algebra that you should be able to do. Um, if you can't do that, you know, it's in this case it doesn't matter, and in most chain rule cases, being able to do this from this will not matter at all. But it's just like it's it's nice it's nice to make it look like this instead of like this. Okay. This time, uh, square root. So what I do with square roots is I just instantly convert them to exponents, because when you're doing chain rule, you're thinking in terms of exponents and not in terms of a square root or a cube root. So you should also see that these things are multiplied here, because obviously, and by that you have to use product rule. So x cubed, actually I'm going to do that last, 3x squared times 5x, or no, 5 minus x to the 1 half, plus x cubed times, okay, so 1 half out in front, 5 minus x, and then minus 1 from 1 half is negative 1 half. And then derivative of the inside, because we just did power rule, is negative 1. Oh, yikes. Oh, yikes. Negative 1. So this would be a correct answer, but it's like, would whether or not AP would count this specific one as right, I would not know, because it would probably depend a little bit uh, on the year, but like doing negative 1 times something, especially with a negative square root, is pretty obvious, and it's not, because AP will take off if you do 2 to the 6 and you leave that in your answer and you don't convert it to 1/3. I have heard of AP taking off there. Um, Something like this, I don't know if it falls into the realm of it's obvious simplification, but I'm gonna say it does, and I'm just gonna do it safe. I would lean, if I was taking the test and I didn't see that and I got it wrong, I'd be like, yeah, that's kind of ridiculous, because I said so. But yeah, I just don't think that. I don't even agree with the idea that simplification should count as an error. Like when, it's like you know giving a ticket to like freaking Dale Earnhardt Jr. for going too fast. It's just like, what? Like, I thought that most calculus students were beyond the realm. So this is your answer, by the way. We're beyond the realm of like losing points because they don't simplify a fraction that they've probably seen more times than like half the kids at their school. So, nah, rant. Find equation of the line tangent to the curve, or a line, I guess, of a line tangent to the curve. Uh, that. So when you're doing stuff that's tangent to a curve, you need a slope and a point. We have like half of a point here, and then the form in which this is in is really good, because we can just straight up take a derivative, because dy dx is already, or y is already on the side, if that makes sense. Y is already alone. So when we take the derivative of this, if you know like a little bit of implicit differentiation, you know that the derivative of y is just dy dx, which is equal to your slope. Um, so That's what I'm gonna do. Just take the derivative of it to find your slope, because that's what a derivative is. Chain rule, I guess. I guess that's how they related it. And then, I just did power rule times the derivative of the inside, which is just 3. So 9 times 3x minus 1 squared is equal to dy dx. And then, since it's at point 1, I need to plug in, or it's at x equals 1, I need to plug in 1 for x, which is 9 times 3 minus 1, which is just 2, squared equals dy dx. And this is just 9 times 4, which is 36. So 36 is your slope. Now I need to find the y part of this coordinate. So I'm just gonna plug in 1. I'm probably not like, if I was taking the AP exam, I would not even show work here. Well, I would have to, I guess, or else I miss the point, because these guys are, I don't know. I could get the right answer somehow, but I can't. I don't have to. Whatever. It's like you get the right answer, but you don't show a freaking coordinate of this. You don't show 2 to the freaking cube. This is freaking 8. 3 times 1 minus 1 to the third is 8. So your point is 1/8, and your slope is 36. So you're just gonna don't use y equals mx plus b form initially. It's harder to do it, and I don't even think that it's even possible to do it initially. Um, I'm sure you could do it if you guess and check constantly, but screw that. Um, or if you got x equals 0 as your thing, you could do it, because then you would just instantly get the y. You could do it if you applied your slope to your point and then went back however many you needed to go back to get 0. But screw that. That's dumb. I'm gonna use Pointslope Form because it's smart. Pointslope Form, by the way, if you don't know it, let me write this in a different color. Um, is y minus y1 equals m times x minus x1. So the y1 and the x1 signify your coordinates. So essentially, it's saying uh, y minus my y coordinate equals my slope times x minus my x coordinate. Um, 36 times x minus 1. This is a right answer. You do not need to turn it over and make it into y equals. You could write this on any exam that you will ever take for calculus, and you will get this right if you write it like this. Hell, any math exam, I would argue, unless it says put it in y equals or y equals mx plus b form, I would just leave it like this. If I was given the same set of conditions and the same um, and I needed a point and a slope and etc. If I got into this form before y equals mx plus b form, I would leave it as this, because this is a right answer. This is a true statement, and this means the exact same thing as y equals mx plus b. So if you know how to do this, don't even bother doing your distribution and then you're moving over of your y coordinate, because it's not worth it, and making a mistake in this uh, at this point would be like, I couldn't even imagine, especially if it was like an actually hard problem. If I got this far and then made a mistake putting it into y equals form, or y equals mx plus b, I'd be so mad. Anyways, that was chain rule, and that stuff is really not that hard. I hope you don't find it that difficult. If you do, there's plenty of resources. It's really, a lot of students do find it to be quite difficult, just because it's so it makes chain rule problems have a special look to them. They look really hard because it's like, oh, all these x squareds, all these x to the fourths times square roots, and all this needless stuff that you completely just bypass with this rule. It's a lot like use substitution and integration by parts in when you get to integrals, because it just makes a problem that seems hard, you just completely just simplify it into like you can simplify like these crazy trig stuff into just like integral of u squared. It's yeah, it's just it's really satisfying to see an integration or a derivative that used chain rule incorrectly. It's really satisfying to see some hard derivative that seems really hard go really easy because of it. So I hope you enjoy this rule as much as I do, and I hope that you at least learn something that you didn't know about this rule, because this is one of my favorite things about calculus.